In this segment, we'll talk about the Runge-Kutta second order method of solving ordinary differential equations. We'll look at the theory behind it. So the kind of differential equations which we solve are of this form, which is the same as the Euler's method. So nothing has changed so far as the format or the form of the differential equations we solve. They're still first order with this format. And what we are doing in the Runge-Kutta second order method is to find a better approximation than Euler's method. So in order to be able to do that, what we do need to do is talk about the application of Taylor series to derive the Runge-Kutta second order method. So if you look at the general form of the Taylor series, it is given by this form here, that although this may not be familiar with you, but it is just another form, same form, that hey, if I know the value of the function at a single point, and I know all its values at all its derivatives at that particular point, I can find the value of the function at any other point. So what we are doing here is that we are finding these values, and if I'm at the point x of I and I need to go to the point x of I plus 1, I just need the value of the derivative of the function at at just one point x of I. So if you look at this way, we can also say this is y sub I, but what is dy by dx? dy by dx is nothing but the value of the function f, so I can rewrite it as f of x of I comma y sub I. And we also know that this is nothing but the step size, so I can substitute h here. Then I get 1 by factorial 2 f prime of x of I comma y sub I, and then it'll be h squared there. Then we have 1 by 3 factorial second derivative of the function f, because if this is the first derivative of function f, this will be the second derivative of function f with respect to x, of course, and so on and so forth. So those are the infinite terms of the Taylor series which we have. So one of the challenges which you are facing here is that although you can see that the first two terms are basically Euler's method being derived from Taylor series, that if we want more accuracy, and that is why we call it a second order method, that we need to take one more term of the Taylor series. We need to include the third term of the Taylor series. But the challenge there is that, hey, we have to calculate f prime, and that we have to do symbolically. So for example, if somebody said, hey, so this is an example, your differential equation given to you is like this one. Then in this case, what will happen is that is the function f, which we call the function f. Then if we have to find f prime of x comma y, then we'll have to use some kind of a chain rule. That will be del f by del x plus del f by del y times dy by dx. And del f by del x in this case is minus 5 e to the power minus x. And del f by del y is minus 3, and dy by dx is already here, so it'll be 5 e to the power minus x minus 3y. So you can very well see that this can create an issue in a numerical method, where in order to be able to apply it, you have to find something symbolically. And this is where Runge and Kutta stepped in. They said we can give you second order accuracy without having to calculate the first derivative of the function f. And that's what we're going to do in the next slide. So this is what Runge and Kutta did. They wrote the formula like this. So since they wrote the formula like this, one would say that, hey, they have introduced 4 unknowns, a1, k1, a2, and k2 right here. So I somehow need to know what those are. And they said, hey, k1 is nothing but the value of the function at function f at this point. and k2 is nothing but the value of the function at this point. So what this quickly tells you is that, hey, this is no longer unknown. K1 is no longer unknown because the value of the function at that particular point. K2 is not an unknown till the time we know P1 and Q11. So basically you have 4 unknowns. A1, A2, P1, and Q11. And if you recall the first 3 terms which we had of the Taylor series, they look like this. And then of course we have the order of the h cubed terms which are left over. So this is what was suggested by Runge and Kutta, that we're going to take this and we're going to equate it to this. You see the left hand side is the same, the right hand side is the same so far as this part is concerned. And what they want to do was that, hey, if I equate this with this and somehow I'm able to find the values of A1, A2, P1, and Q11, then when I am using this particular formula, there is no mention of the first derivative of the function f, hence making it a numerically strong technique to use. So when they equated these two expressions, and I'm not going to give you the proof for it, the proof is in the textbook, that they found out that, hey, you get 3 equations. You get A1 plus A2 equal to 1, you get A2 P1 equal to 1/2, and you get A2 Q11 equal to 1/2. Those are the 3 equations which you get. And now you might wonder that if I get 3 equations and I have 4 unknowns, what have I solved? You have solved the 4 unknowns by saying that, hey, I will take one of the unknowns to be something which I know. So for example, if you choose A2 equal to 1/2, then you get the values of A1 equal to 1/2, P1 equal to 1, and Q11 equal to 1. And you can use those, and then you know all the 4 unknowns. So that's why if you look at a textbook or look at the internet about the Runge-Kutta second order method, you will see various forms of it. And the 3 most popular ones are Heun's method, midpoint method, and Ralph's method, which are basically taking different values of A2. So I'm going to show you Heun's method. You can do Ralph's methods and midpoint method formulas yourself. So let me show you what is involved in the Heun's method. What we have is that A2 is chosen as 1/2. And if you look at the 3 equations which we had, which need to be satisfied to get the second order accuracy, we had these 3 equations. So if I choose A2 equal to 1/2, from here I'll get A1 equal to 1/2. From here I'll get P1 equal to 1, and from here I'll get Q1 equal to 1. So that means that A1 is 1/2, A2 is 1/2, P1 is 1, and Q11 is 1. So if I substitute back into the general form which they have for the Runge-Kutta second order method, I'll get y sub I plus 1 is equal to y sub I plus A1, which is half, times K1, plus A2, which is half, times K2 times H. What K1 is nothing but the value of the function at x of I, y sub I. And K2 is nothing but the value of the function of x of I plus H, because it's P1 times H. P1 is 1. Y sub I plus Q11, which is 1. K1 times H. And that's your Heun's method. That's your Heun's method, saying that, hey, if you want to find an approximate value of y at a point ahead, if you are at x of I and you want to go to x of I plus h or x of I plus 1, then what you have to do is you have to find the slope k1 of y with respect to x, and that's given by the function f. You have to find the other slope k2, you give it equal weightage of half, and you multiply by the step size, add the value of y, which was the value of y at x of I, and you get an approximate value of the y value at the point ahead. Now look at this. This one is a slope at the current point, or at the point where you are, x of I, and this one is the slope at x of I plus h, which is the point where you want to be. And in order to find the value of the slope f, you also need the value of y. And how is that approximate value of y calculated? That y is calculated by using the Euler's method formula. As you can see here, is y sub I plus k1, which is nothing but this, times h. So what you're basically seeing is that the Runge-Kutta second order method is simply finding slopes at 2 points, giving it some weightage to each of the slopes, and still getting second order accuracy. And that is the beauty which we need to appreciate as numerical method students. The other two methods which are very popular, one is called the Ralston's method, and you can do it yourself or you can look at the textbook. And in that case, the value of A2 is chosen as 2/3. The other one is called the midpoint method. And in the midpoint method, one chooses A2 equal to 0, A2 equal to 1. And based on that, whatever formulas, resulting formulas you get, you are able to. They look very similar to what we did for the Heun's method, but they are simply functions being calculated at different points, different weights being given to the slopes. And that is the end of this segment.